Indeterminate axially loaded elements, by definition, are the elements where we cannot determine the internal forces just by equilibrium equations. We have learned in statics that if we want to determine the internal force in the element, we can use the free body diagram. Free body diagram means that we are going to cut the elements and use the equilibrium equations. Sum of the forces in the x direction equal to 0, sum of the forces in the y direction equal to 0, or sum of the moments is equal to 0. With those three equations, we can determine the internal forces. But that's not the case for all the problems. In some cases, we cannot determine the internal forces just by equilibrium equations. And that's what we want to talk about today. Let me show you one example. There are 4 cases that you wanted to determine the internal force in those 4 cases. The first case is one element that is not fixed and is subjected to a force on the right side. The second case is similar to the first one, but it is supported on the left side. The third one is similar to the first 2 cases. It is supported on the left side, but there is an additional element added to the right part of that, which is shown in red. The location of F is going to be the same as the previous case. And the last one is similar to the third case, but the right side is fixed. Okay? So we want to determine how much would be the internal force in these 4 cases. To understand how can we solve these types of problems, we always need to use the free body diagram, which means we need to cut the element at this section that you want to determine the internal force and then use the equilibrium equation. Let's do that for element number 1. If we do that for element number 1, we would come up with 2 sides. If we consider the left side, how much would be the force acting on that part? It is 0. So if I say at the cut section, I'm going to put one unknown force. Let's call this F1. 1 stands for the internal force in element number 1. And then write down some of the forces in the x direction. We would end up F1 equal to 0. This problem is statically unstable, which means that it is not stationary, it is moving. We can't determine how much is the force here because it depends on the acceleration and the mass of the element. But there is no internal force based on static. Okay, so that would be case number 1. In case number 2, it is restrained on the left side. So if we cut the element into half, there are 2 parts. Which side can we consider for determining the internal force, left or right? We have to consider the right part because that is the free part. If we consider the left side, is it free? No, so this is not free body diagram, so I have to consider the right part. This is the free body. The external force is F, and there will be one internal force, which we call this F1. F1 is always outward from the surface. So write down some of the forces in the x direction. We would have F1 would be equal to F, and that gives us the internal force in the element. So this is no surprise that the internal force would be equal to the external force acting on the element. That would be case number 2. Now let's talk about case 3, where we have one additional element to the right of that. Again, we are going to use the exact same concept. We are going to cut the elements number 1 and draw the free body diagram. Put the external force and internal force. Internal force is going to be outward from the surface. If we write down the equilibrium equation in the x direction, how much would be the internal force? That's going to be the same as case number 2. That additional part is not going to add anything into the equation, so internal force is going to be F, right? Now let me ask you this question. How much would be the internal force in the red element, element 2? 0. There is no internal force on that part. If you cut that, you will see that there is no force acting on that part, right? Okay, now we get to the last part. We are going to cut the element. If we cut the element, just the blue element, is that part free? Both sides are restrained, so we need to have one additional cut to make the middle part free. So I have to cut it twice as shown here, and then there will be 2 internal forces. Both of them are outward from the surface. We're going to call them F1 and F2. Then if we write down the equilibrium equation in the x direction, we would have F1 with the negative sign going to the left side plus F plus F2 is going to be 0. So in that case, there are 2 unknown, F1 and F2, and those are going to be equal to F. So in that case, we have 2 unknowns and just 1 equation. So this problem is indeterminate. We cannot determine the internal force just by the equilibrium equation. So I just wanted to give you an example on the cases where the problem is indeterminate. All right, if we were in statics, this problem is unsolvable forever. We cannot determine how much is the internal force using the equilibrium equation. However, in mechanics of materials, knowing how much are the deformations, we can determine the internal forces in the element. So let's do that.
The method that we use here for analyzing indeterminate structures is called the compatibility of deformations. In this method, the deformation in each individual element is determined. Then we try to find out what should be the relationship between the deformations in order to make them compatible with the given restraints of the structure. In order to be able to solve this problem, we have to have some extra information such as area of the elements or mechanical properties or the length of the element. Here I'm assuming some numbers in order to be able to solve the problem numerically. Also, I'm going to write down the equilibrium equation that we developed for this structure. And we know that this equilibrium equation is not sufficient because there are two unknowns and there is just one equation. We need to guess the extra equation from the compatibility of deformations. In the second step, we determine the internal deformations in each individual element. We have already learned that the deformation in the axially loaded element is determined from the Flee equation. Delta is FL divided by EA. And after plugging in the values, we can determine how much is the internal deformation as a function of the unknown internal force, in this case F1. In a similar way, we can calculate the deformation in the second element. Delta 2 is FL divided by EA. And I'm going to plug in the associated value of the second element in order to determine the deformation delta 2 in terms of unknown force F2. The third step is the main part of this problem. We need to figure out what should be the relationship between the deformations. Look at this problem from physical point of view. Force P is acting on pulley B. It is compressing element number 2, but at the same time it is putting element number 1 in tension. In other words, element 1 is getting longer, but element 2 is getting shorter. Because the structure is fixed at both ends, the amount of stretch in element number 1 plus the amount of shortening in element number 2 should be equal to 0. The total length of the system is unchanged. So the compatibility of deformation for this structure would be delta 1 plus delta 2 is equal to 0. Now we are going to plug in the values of delta 1 and delta 2 that we have already calculated step 2 and put them together. And now the magic happens. We got another relationship between force F1 and F2. We got the extra equation that we were looking for. Now we can combine these two equations together in order to calculate how much is F1 and how much is F2. This is what we do in step number 4. In step 4, we are going to combine the equations that we got in step 1 and step 3 together in order to solve it for the internal forces. And that's it. We have determined the internal forces in an indeterminate axially loaded element. Okay, so let's see what we have done for this problem. In this problem, there were two unknowns, but we had just one equation from the equilibrium. So the problem was indeterminate statically. In order to be able to solve the problem and determine the internal force, we needed to get one extra equation. And that extra equation came from the compatibility of deformations. First, we calculated how much is the internal deformation in each individual element in terms of the internal unknown force. Then we tried to find out what should be the relationship between the deformations in order to make them compatible with the given restraint of the structure. Then we combined these two equations together and solved it for the internal force. This topic could be a bit tricky, so it would be good for us to practice another problem, which is probably more complex, in order to make sure that we understand the concept of the compatibility of deformations for analyzing indeterminate axially loaded elements.
Consider this problem where a rigid element AB, which is horizontal, is subjected to a force of P, and there are two columns that are supporting that beam. The magnitude of the force is given to be 100 kilonewton. The length of those legs or columns is given to be 3.5 meter. The area of each of those columns are given 850 and 600 square millimeter. And the location of force P is also shown. I want to determine how much would be the internal force in each of these legs. In order to solve this problem, again, we need to use the free body diagram, which means that we need to cut the element from two legs, given force P, and there will be two unknown forces on those elements. I'm going to call them F1 and F2, and those are going to be outward from the surface. Okay? I know that in the reality they are going to be upward, but we are going to put them always outward from the section, and then if we get negative sign, that means that the element is going to be in compression. Alright, now we are going to use the equilibrium equations. I'm going to start with some of the moments about A. We would get P multiplied by distance of P to the A, which is 2 meter, plus F2 multiplied by distance of F2 to A, which is 2 plus 5, or 7 meter. Sum of these two is going to be equal to 0. P is given from that equation. I can determine F2. In a similar way, we can determine internal force in element number 1 using sum of the forces in the y direction. P plus F1 plus F2 is going to be equal to 0. F2 is already negative and determined, so I can determine F1 based on the other two variables. So we have determined the internal forces in these two elements. Negative sign in these cases means that the element is going to be under compression. Alright, the problem was determinate, and I could determine the internal forces just by equilibrium equations. Alright, the other problem would be similar to the previous case, but I'm going to add one more leg at point C. Okay? So we want to see what would be the effect of adding that leg into the calculation. Again, let's start with the equilibrium equation. I'm going to cut the element, and there will be external force and three internal forces here, which we are going to call them F1, F2, and F3. Now, if we write down some of the moments about A, F1 is cancelled, P is given, but there will be two unknowns, F2 and F3. So let's plug in the values. P is 100, multiply that by 2, plus F3 multiplied by 4.5 meter, which is distance of C to A, plus F2 multiplied by 7 meter, which is distance of B to A. And that's going to be equal to 0. So we can see that there is one equation and two unknowns. Alright, we are going to call this equation number 1. The other one would be sum of the forces in the y direction. In that case, we would have three unknowns, F1, F2, and F3. From that, we get another equation, but these two equations are unsolvable because the number of unknowns is higher than the number of equations that we have here. There are three unknowns, F1, 2, and 3, and there are just two equations. So how can we solve this problem? We need to use deformation and the compatibility of deformations. The number of unknowns here are 3. I'm going to call that n sub r. And the number of equations is going to be 2. And I'm going to call that n sub e. The degree of indeterminacy would be the difference between these two values. nr minus ne would be the degree of indeterminacy. In this case, the problem is 1 degree indeterminate, which means that we need to get one extra equation to be able to solve this problem. Alright, now I need to use the deformation in each element. Let me use the force-displacement relation that we have learned before. Deformation in element number 1 is delta 1. Delta 1 is F1 L1 divided by E1 A1. If I simplify that, that would be F1 divided by 34,000. Delta 2 would be the same, FL over EA for the second element. If I plug in the values, that simplifies to F2 divided by 24,000. In a similar way, we can write down delta 3 as FL over EA. Plug in the values, we would get F3 divided by 20,000. So, we have determined the deformations in terms of the internal forces, which are unknown. Now we get to the most important part of this problem, which is finding a relationship between the deformations, which is called the compatibility of deformations. Here I need to find a relationship between those deformations. Say force P is pushing that element downward. That is a rigid element, so that remains as one straight line. One side is going to be pushed more than the other one. Let's assume the left side is going to go downward more than the others. You can assume any side you want. That's not going to change the answer at the end. You can assume the right side is going downward more than the others. At the end, you're going to get the same answer. Okay, now what are the relationship between those deformations? Let me look into that in details. This is the original position of that rigid element. After deformation, it has moved downward like this. The deformation at the very left end is delta A, at C is delta C, and the right side is delta B. We have determined those deformations, right? Knowing those deformations, I can find a relationship between these values by using similar triangles. But where is the triangle here? Let me draw a line like this. We can see the two triangles here. So I'm going to redraw that triangle down here. The deformation on the left side is delta A minus delta B, and the deformation at the middle part is delta C minus delta B, right? Now I'm going to write down the compatibility of deformation. The compatibility of deformation is going to be delta A minus delta B divided by the entire length, which is 7 meters, is equal to delta C minus delta B divided by the length from C to B, which is 2.5 meters. We found a relationship between these parameters. Let me simplify that, and we get this simplified form. All right? And that would be the relationship between the deformations. Now I'm going to plug in the values of deformations that we obtained in the second step into those equations. So there is no gap here, so delta A is going to be equal to delta 1, delta B is going to be equal to delta 2, and delta C is going to be equal to delta 3. Now I'm going to plug in the values into this equation. What did I get here? This is where the magic happens. I found another relationship between those forces. Let me simplify that. This is the third equation that we were looking for. We have the third equation here. We have the two equations in the first step. The last part would be simply putting them together and solve the system of three equations and three unknowns and solve it for force. Okay, I'm going to combine 1, 2, and 3. And from that, we can determine F1 is equal to negative 63.8. F2 is going to be negative 14.8. And F3 is going to be 21.4 kilonewton. Okay? We have determined the internal force in these elements. All right. Now let's compare the answers from this case with the case that we had here. In this case, the force in element number 1 is 71. Once we added another leg, the internal force has reduced to 63.8. So the force has reduced. It makes sense because we added one more leg. But what is the cost of that? The calculation is much more complicated because we have added one more element. Okay? So what was the degree of indeterminacy for this problem? 1. What is the typical degree of indeterminacy in problems that we have in engineering world? Do you have an estimate? Say if you want to design a building in this size, like this building, what would be the degree of indeterminacy for our structure? Give me a number. 100, okay? Go up. So for this structure, the order is about like 10 to 100,000 degree of indeterminacy. And in the complicated structure, we can easily get to more than 1 million degree of indeterminacy. So how can we solve those cases? In the past, engineers used to solve those cases by hand. Now, we don't have to do that. We use computer, but we should know how computer is doing that because we are going to give instruction to computer to do that. So that's why we need to understand how these are working. Okay, let me quickly wrap it up. For solving indeterminate axially loaded elements, there are 4 steps. The first step would be using the equilibrium equation to determine the forces. In order to do that, there are typically 3 equations. Sum of the forces in the x direction equal to 0, sum of the forces in the y direction equal to 0, and sum of the moments are equal to 0. And if those are sufficient for determining the internal force, good. the problem is determinate. If the number of unknowns is more than the number of equations, the problem is indeterminate. So if n equal to 0, the problem is determinate. If n is larger than 0, that means the problem is indeterminate. The second step would be finding the deformations in terms of force, and for that we use delta is FL over EA. Alright, the third step would be the compatibility of the deformation, which is the main part of solving these types of problems. There are three different categories. Category number 1 is where the elements are connected head to head, like this case, or this case, or this case. In all of those, the elements are connected head to head. The compatibility of deformation is delta 1 plus delta 2 is equal to 0, because they are both fixed at the ends. What if there is a gap? In that case, delta 1 plus delta 2 is equal to the gap. Alright, second category is the case where one element is inside the other one, or they are connected fully together, like this one, or this one, or this one. In these cases, the compatibility of deformation is delta 1 is equal to delta 2. They both have the same deformation. If there is a gap, we need to add the gap to one side, depending on the problem. It could be on the right side or on the left side, depending on how they are connected together. The third case is the one that we just talked about, where we need to use similar triangles.
And the last part is combining the equations that we got from equilibrium in step 1 and the compatibility of deformations in step 3 together in order to solve it for the internal forces. And that's it. This is the process for analyzing indeterminate axially loaded elements. Thank you very much, and I'll see you later.